Hello, George Notchik here again. In a previous video, I discussed how we might find the value of this improper integral on e to the minus t squared. And after I posted that video, somebody asked, why don't I try using Laplace transforms? And that's what this particular video will discuss, is Laplace transform and how we might be able to solve an integral of this type using Laplace transforms. In the previous video, the way we solved this integral is we converted it into a multi-valued integral, double integral, changed coordinate systems and limits into using polar coordinates, and we solved it using polar coordinates, and we found that the value was the square root of pi over 2. But we can write this improper integral as a limit of a function g of x. We define g of x as the integral from 0 to x on e to the minus t squared dt. The t is the dummy variable in the integral here. And we have a variable limit on x. So this improper integral is nothing more than the limit of g of x, this particular integral, as x gets very large. X tends to infinity, then the upper limit becomes infinity, as in the original integral. But before I get into the Laplace transform method of solving this particular integral, let's first discuss the error function and the complementary error function, because they're both going to appear in the analysis. The error function, as you remember, is ERF of x, which is 2 over the square root of pi, the integral 0 to x e to the minus t squared dt, or in this case it would be 2 over the square root of pi times g of x, this particular integral there. Now the complementary error function is designated as ERFC on x, which is just 1 minus the error function. So this will end up being the limit, or the integral on the limit from x to infinity of 2 over the square root of pi e to the minus t squared dt. So if you consider, for example, let's look at 2 over the square root of pi on the integral 0 to infinity, the original integral that we have. We can write this, we can split it up into two integrals. One will go from 0 to x on e to the minus t squared, and then the other integral will go from x to infinity on e to the minus t squared. So what I did is I broke the integral up from 0 to infinity into two integrals, 0 to x and then from x to infinity. Well, this, we see, is nothing more than the error function. That the error function goes from 0 to x, and this is the complementary error function. It goes from x to infinity. So then, we know from past experience that the error function when evaluated at x equals 0 is 0, and when evaluated at infinity it's equal to 1. Now we also know from here that this portion is a square root of pi over 2, and if we multiply by 2 over the square root of pi, this whole thing is equal to 1. So we see that the error function plus the complementary error function is equal to 1. Hence, the complementary error function is just 1 minus the error function. So this is what we have with the error function and the complementary error function. Their sum is equal to 1. And we can easily see that if we graph the integrand e to the minus t squared. Or I will use the factor 2 over the square root of pi times e to the minus t squared. Well, when t is 0, e to the 0 is 1, so the value of the function will be 2 over the square root of pi at x equals, or t equals to 0. Then, as t increases, e to the minus t squared rapidly decreases and asymptotically approaches 0. Now, this portion of the area under the curve from 0 to x is the error function. The error function is the area under the curve of 2 over the square root of pi e to the minus t squared from 0 to x, and the complementary error function is just the remaining area from x on out to infinity. So the sum of the two is the total area under this curve, which is 1 because we have the scale factor of 2 over the square root of pi in the multiplying out on the integral. So all we need to know at this point is that the error function plus the complementary error function is equal to 1. And now we'll look at solving this integral using Laplace transforms. The Laplace transform on a function g of x is defined as, we use a capital script L to denote the Laplace transform. The Laplace transform on a single variable function g of x is the integral from 0 to infinity of e to the minus sx times g of x, and we integrate with respect to x. And the e to the minus sx is what we call weighting function. This weighting function is put into the integrand to ensure that the integrand is going to be of what we call exponential order, and it forces convergence of this particular integral. And what happens here is the integration with respect to x, since we're evaluating between two definite limits, 0 and infinity, the x gets integrated out and we're left with a function of x, s. And we denote the Laplace transform as capital G of s. So we start with small g of x in the x domain. We perform the Laplace integral, and we get a new function called cap g of s because the x gets integrated out. Now, also in the Laplace transform theory, we have what's called a Final Value Theorem. Called the Final Value Theorem. And in the Final Value Theorem, tells us that the limit of g of x as x goes to infinity is the limit of cap g of s times s as s goes to 0. So we can find the final value in the x space on g of x as x goes to infinity by knowing the Laplace transform of g of x and multiply by s and take the limit as s goes to 0. So if we know the Laplace transform of a function and we want to find its final value, all we have to do is multiply by s and take the limit as s goes to 0. Now, Laplace transform also has an interesting property that if g of x is an integral, say 0 to t or 0 to x of f of t dt, that our g of x is the integral of some function f of t from 0 to x, then the Laplace transform of g of x, which is now cap g of s, is nothing more than the Laplace transform of the integrand. And we divide by s. So whenever we have an integral and we take the Laplace transform, all we have to do is know the Laplace transform of the integrand and divide by s. Where now f of s is the Laplace transform of f of t, the integrand. We take the integrand, we determine its Laplace transform, divide by s to get the Laplace transform of the integral of f of t. Now, this gives us an interesting result. If we want to find the Laplace transform of the improper integral that we have here, let's apply this particular theorem and see what happens. So, here we have g of x is this particular integral, which is the same as this, where f of t is e to the minus t squared. Now, let's look at this first in general. Let's apply the final value theorem to the integral of f of t. We're going to look at this and apply the final value theorem to it. So the limit on g of x as x goes to infinity, that's what we're going to want to find the Laplace transform of, is then the limit of g of s times s as s goes to 0. But what is g of s? G of s is, we have the limit of s, but cap g of s, the Laplace transform of the integral, is nothing more than the Laplace transform of the integrand, f of s, and we divide by s. The s's cancel, and we end up with a limit of f of s as s goes to 0. So we have a very interesting result here, is that the limit on g of x as x goes to infinity, where we get an improper integral from 0 to infinity on f of t, is the value of that integral then will be nothing more than the limit of the Laplace transform of the integrand as s goes to 0. So if we know, in this case, our g of x is going to be this integral where my f of t is e to the minus t squared, if we determine and know the value of the Laplace transform of e to the minus t squared, and we want to find the value of this limit of this integral, and the limit is x goes to infinity, all we have to do is take the Laplace transform of e to the minus t squared and take the limit as s goes to 0 on the Laplace transform of e to the minus t squared. Now, so the trick is, how do we find the Laplace transform of e to the minus t squared? Well, you can either compute it directly, which I will do at the end, or you can have, like I do, is a book of tables of Laplace transforms, what we call transform pairs. You have functions in the x domain or in the t domain, and it gives you, in the table, you look up the function you want, and then it gives you the Laplace transform. And this book has like over 300 pages of different functions and transforms. For e to the minus t squared, this book is Robertson-Kaufman, Table of Laplace Transforms, and on page 20, form number 2, you can see here that we have e to the minus t squared over a, where a is a constant, and here is the Laplace transform. Now I'll write that down. So we want to know the Laplace transform e to the minus t squared over a. This is in the book. And this is given as the square root of pi times a over 2 e to the as over 2 squared times the error function, complementary error function, of s square root of a over 2. This is a little different than the form that it was given in the book, because what I did is I just combined the factors and put it all under the square and the square root. But it's the same form that's in the book. Now, if we put in a equal to 1, then the Laplace transform v to the minus t squared will just be, when we put a equals to 1, we'll end up with the square root of pi over 2e to the s over 2 quantity squared, the error function, complementary error function of s over 2. Now, in order to find the value of a of the improper integral, we take the limit of this general function g of x as x goes to infinity. We just showed that it's the limit of the Laplace transform of the integrand as s goes to 0. So all we have to do is find the Laplace transform of the integrand of this integral. That's what we're doing here, finding the Laplace transform of the integrand. We don't have to worry about the integral because we know that the Laplace transform of the integral is just the Laplace transform of the integrand divided by s. And with the final value theorem, we had that the Laplace transform, or the limit of g of x as x goes to 0, is just s times the Laplace transform of the integrand divided by s, and the s is cancelled. So it's just the limit on f of s, which is the Laplace transform of the integrand as s goes to 0. So all we have to do now is find the Laplace transform of e to the minus t squared. And what I just showed is from the tables of Laplace transforms in Sanders and Kaufman, is that we have the Laplace transform of e to the minus t squared over a is the square root of pi a over 2 e to the as over 2 quantity squared, the error function of s square root of a over 2. Now, the error function 0 is equal to 1, and the complementary error function at infinity is equal to 0. It's just the opposite of the error function, and we saw that by, if you look at e to the minus t squared, that the function goes down like this. The complementary error function is just the area on the tail of the function between 0 and infinity as we go out to infinity. So when x is 0, we're looking at all of the area under the curve, which gives us 1. And as x tends to infinity, there isn't any area left under the curve, so the complementary error function is 0 at x equals infinity. So now, let's find the value of the limit of the Laplace transform of e to the minus t squared as s goes to 0. So here's our Laplace transform of e to the minus t squared, and as s goes to 0, we have e to the 0, which goes to 1. Oops, I'll call that 1.0. So e to the 0 goes to 1. The error function at 0 is also equal to 1. So that goes to 1. So what are we left with? We're left with the square root of pi over 2, which is the value that we got when we performed the double integral by introducing a multivariable representation for a squared. So we get the same value, and as we can see, if we know the transform of the integrand, it's very easy to find the limit. All we have to do is take the Laplace transform of the integrand and take the limit as s goes to 0 to get us the value of the improper integral. Now, the question is suppose I want to find the value of this general function where x has a where the upper limit is variable as x. What is g of x for this particular integral? Well, we can use Laplace transforms to find that, and that's what I'll do now, is find the value for g of x for this particular integral. Okay, now I'm going to look at the general integral, where we have g of x is equal to the integral from 0 to x of e to the minus t squared dt. We want to find what g of x is, And we're going to use Laplace transforms for doing that. Now, remember that this is of the form 0 to x of some f of t dt. This is the integral of some function f of t, which is f of t is just e to the minus t squared. Now, when we take the Laplace transform of g of x, this is just the Laplace transform of the integrand divided by s, because we're integrating f of t. So the Laplace transform of an integral of f of t is just the Laplace transform of f of t divided by s. Now, we just showed from the table of transforms is that we want to find f of s, which is the Laplace transform of f of t, which is the Laplace transform of e to the minus t squared. And from Sanders and Kaufman tables, we got that the Laplace transform of e to the minus t squared is the square root of pi over 2 times e to the s over 2 squared times the complementary error function of s over 2. That's the Laplace transform of e to the minus t squared. Now, the Laplace transform of the integral, g of x, is just this transform. This is f of s. So we divide through by s. We end up with square root of pi over 2 e to the s over 2 squared times the complementary error function of s over 2, and we divide by s. Now, we are in what's called the s domain, the transform domain, and we need to get back to the x domain. And the way we do that is, this is the transform function, and g of x is just the inverse Laplace transform of g of s. We're going to go back into the x domain, so we have to take the inverse Laplace transform of g of x. And the way we do that is we go to the book of transform pairs, and on page 316 on form 16312 is, if we see here, this particular one, this is of the form that we're looking for. We have 1 over s e with s squared and the complementary error function of s. Here we have a coefficient a, which will be equal to 1/2 for the problem that we have. And then back to the x or the t domain, it's the error function of t over 2a. So if we use the from the transform pair, is what the book gives us is that e to the as squared times the complementary error function of as divided by s. This goes to the error function of t over 2a. Or in our case, the t will just be x. So this will be x. We're going to be in the x domain. So we compare the forms. In this case, a is going to equal 1/2. So using the form here, we have e to the s over 2 squared. I'm putting a equal to a half. The error function of s over 2 divided by s, and this will go to the error function of x over 2 times 1/2, or it's just, those cancel, and it's just the error function of x. Now, the only difference between these forms is that we have a square root of pi over 2. So we multiply both sides by square root of pi over 2. So in the inverse transform, g of x then is the inverse transform of cap g of s, which is this form. So the inverse transform of this is just the error function of x, and then multiplied by square root of pi over 2. So that is the value of this function. If we integrate out e to the minus t squared from 0 to x, this is the result. It's the error function of x times the square root of pi over 2. And again, as we take x goes to infinity to get the improper integral, the error function on x as x goes to infinity is equal to 1. So that just becomes 1. So the limit on g of x, if we take this, the limit of g of x is x goes to infinity is just the limit of the error function on x as x goes to infinity times the square root of pi over 2. And the error function on x as x goes to infinity, that goes to 1. We're left with the square root of pi over 2, which is the value of a that we had originally. So the question comes up that when we're dealing with Laplace transforms and we're in the S space, the transform space, and after we've done all our manipulations, how is it we get back to the original space? We can use a table of transform pairs like I showed you, but if you don't have that, then you have to use what's called the inversion integral to get back to do the inverse transform on the function of s to get back to a function in x. And this is how a lot of the transform pairs are computed in these tables, and it's a fairly complicated process. What you use is what's called the inversion integral. Suppose we have a function g of s. We're in the transform space, and we want to take the inverse Laplace transform to get g of x, small g of x. Well, we had this function here, where we had pi over 2 e to the s over 2 squared, the complementary error function of s over 2 over s, and we need to take the inverse Laplace transform. Well, we did that by using the table of transform pairs, but to compute it directly, you have to use what's called a contour integral in the complex plane. The inversion integral is 1 over 2 pi I, where I is the complex unit of square root of minus 1. We take the limit as cap t goes to infinity as we go from gamma to minus I over 2 to gamma to plus e to the cap t g of s ds. This is called the inversion integral. Now, the inversion integral, like I said, is a contour integral in the complex plane. And the inversion integral is computed along a vertical line, which is the real part of S, which is gamma, and such that the gamma has to be greater than the real part of all the singularities that g of s possesses in the complex plane. And g of s also has to be bounded on the line that we're integrating on. Now, computation of this particular type of integral, this contour integral, is accomplished by using what's called the Cauchy residue theorem. And after you use the Cauchy residue theorem, you generally end up with an infinite series. It's not a closed form solution unless you can recognize the infinite series and sum the infinite series. It might sum to some elementary function or some special functions that you might be able to recognize. But in general, you end up with a infinite series solution. Now, if all the singularities of g of s are in the left half plane of the complex plane, if you remember what a complex plane looks like, you have the real axis, you have the imaginary axis. Now, if all the singularities are off here in the left half plane, then the inversion integral becomes identical to the inverse Fourier transform, because you can set the gamma equal to 0 and it becomes identical to the Fourier inverse transform. In the complex theory of integration, you like to deal with what are called entire functions. An entire function is complex differentiable in the neighborhood of every point in its domain. And this is a very, very strong condition. An entire function is actually infinitely differentiable and possesses a convergent Taylor series in the neighborhood of each point of its domain, and these are called analytic functions. And most of the functions that you deal with fall into that class. Now, I'm not going to perform an inversion integral just yet, maybe sometime in the future, because it's a fairly complicated process. You have to know a lot about complex theory and integrating in the complex plane, contour integration, and the residue theorem. But let's just suffice it to say this is one way that you can get the inverse transform, but it's much easier, of course, to look it up in tables. Look up your function in tables. Now, lastly, what I'm going to do here is directly compute the Laplace transform for f of t, which is e to the minus t squared. We're going to find the Laplace transform of that. Now, f of s, cap f of s, is the Laplace transform of e to the minus t squared, which, remember, is the integral from 0 to infinity of e to the minus st, and then we have e to the minus t squared dt. Well, we have a product of two exponentials, so we can combine the exponents. So we have e to the minus let's write it as t squared plus st dt. We have minus t squared minus st. Now what we do here is we complete the square. T squared plus st is t squared plus st plus s squared over 4 minus s squared over 4. I just added 0. So we can write this as t squared plus st plus s over 2 quantity squared minus s squared over 4. Well, this is a perfect square. This is t plus s over 2 quantity squared, and then minus s squared over 4. I just completed the square. I added and subtracted s squared over 4 so that I could take this portion here as a perfect square. And that's what I have here. So we'll rewrite the integral now. This is equal to 0 to infinity of e to the minus t plus s over 2 quantity squared minus s squared over 4. And we're integrating with respect to t. Well, I can now break this up into two exponents. I've got 0 to infinity, e to the minus t plus s over 2 quantity squared times e to the minus s squared over 4 dt. Now, this portion, this exponential is not a function of t, so I can pull it out of the integral. So we end up with integral with e to minus s squared over 4. That's equals. And then e to the minus t plus s over 2 quantity squared dt. Now we make a substitution. U equals t plus s over 2. So du will be equal to dt. And this is from 0 to infinity. Now, when t is 0, u is equal to s over 2, and when t is infinity, u is also infinity. And then we'll make these substitutions. We'll change the limits. So this now becomes e to the minus s squared over 4 times e, or the integral of e to the minus u squared du. And then the limits go from s over 2 to infinity. And this portion you recognize as being the complementary error function. Okay, so here we are. I made a slight mistake. This shouldn't be a minus sign. This is a plus sign on e to the s squared over 4. So we got to this point. We recognize this as being the complementary error function. So to recap, what we did here is we have a function f of t, which is e to the minus t squared, and we're finding the Laplace transform. This is the Laplace transform integral. So e to the minus t squared here, we multiply by e to the minus st, and then we combined the exponents on the exponentials, completed the square, and then we pulled out the constant term out of the integral. That wasn't a function of t. And then we did a change of variable, changed the limits, and we ended up with this integral. So what we have now, putting up here, is we have cap f of s, which is the Laplace transform of e to the minus t squared. It's e to the s squared over 4 times the integral of e to the minus u squared du from s over 2 to infinity. And we recognize this particular integral as being the complementary error function times the square root of pi over 2. So we have in the t domain, f of t is e to the minus t squared over, or e to the minus t squared. And then we go into the Laplace domain to compute f of s. And f of s, then we find by using the transform integral is the error function, complementary error function of s over 2. So in the t domain, our function is e to the minus t squared, and in the transform domain, it's the square root of pi over 2 s squared over 4, complementary error function of s over 2. Now, Laplace transform techniques are very, very powerful. A lot of times they provide an efficient means to evaluate integrals if you wish to do so. One of the best books on the subject that I ever came across, I had this in graduate school at Michigan Tech, where I did my master's in mathematics in transform theory, orthogonal polynomials, and special functions. And there's a book by Ian Snedden, if anyone's interested, S-N-E-D-D-O-N, Ian, I-A-N. It's called The Use of Integral Transforms, and not only discusses Fourier transforms, but deals with Hankel functions and other types of special transforms. And it's a very, very good book. Now, what I'm going to be doing in a future video is I'm going to use Laplace transforms for solving a differential equation. Remember, in the t domain, say if we have f of t, and we want to go in, we do a transform, and we go into the transform space. This is our transform space here, where we get a function cap f of s. Now, an interesting property of Laplace transforms, remember, is that if f of t is an integral, some 0 to x or 0 to t of some, say, g of x dx, this is just a dummy variable, that in the transform space, the transform function is just cap g of s, and we divide by s because we have an integral. Now, you might also guess that if you have a derivative of a function, say if we're taking a derivative in the t domain, in the transform space, it becomes s times the transform function. So when you integrate, you divide by s. When you differentiate, you multiply by s. If you double integrate, you multiply by s twice. So you multiply by s squared. So if we're going f double prime on t, then it's s squared f of s. And what this does is it leads to a very interesting situation when dealing with differential equations. Laplace transform converts differential equations into polynomials. So solving a differential equation in the transform space is nothing more than doing algebra. You solve for the roots of polynomials, and then there's a procedure that you can use through partial fractions and other algebraic techniques to get your transform function into recognizable form so you can easily transform back into the t domain. So the whole idea in transforms is you start off with some complicated forms in the t domain, you transform into the transform space, you just do algebraic manipulations. If you're integrating or differentiating, if you have a differential equation or a combination of differential and integral equations, you just do algebraic manipulations in the transform space, get into recognizable forms, and then transform back to the t domain. And I've seen on the internet where some people demonstrated Laplace transforms just using simple differential equations, first order differential equation. In the next video, I'm going to solve a third order differential equation with a forcing function and initial conditions and show you how Laplace transforms can solve differential equations. And Basically, it's just a lot of algebra. There's going to be an awful lot of algebra involved in using the transforms, but it's so much easier than trying to work with differential equations in the t domain. You transform it into the transform space, manipulate it, and then go back. We do this a lot in electrical engineering. In fact, electrical engineers call this the frequency domain, where S is a complex frequency. And when dealing with AC circuits, time-varying circuits, you can go directly from your network equation where you have inductors, capacitors, resistors. You can immediately write down the transform solution and then convert it back into the time domain very easily without having to write down any differential equations whatsoever. You can just go directly from the network into transform space and write down your answer and then transform it into the time domain. It's a very, very powerful technique, and in a future video I will solve some AC electrical circuits using Laplace transform techniques. So that about wraps it up here for this video, and I hope it gave you a little bit of insight into the power of transform techniques.